Okay, folks, this is going to be a very quick, or hopefully very quick, explanation of bending stress on an airframe. Now, this is the example that's on page 174, Copeland text. And I'm going to try and also in this video just give you a little bit of revision on the conventions for shear force, whether it's positive or negative, and the conventions for bending moments. Remembering, of course, that when we're dealing with these shear forces and these bending moments, these are internal reaction forces that happen inside the beam as a result of the beam being bent. Okay, so we're going to look at one of the things that we did in year 11 too, which was reaction at the wall and bending moment at the wall for a cantilever, because this problem initially, well, essentially is dealing with a cantilever beam going off to the right. So if this is the fuselage of the aircraft, so the aircraft would be here, and the wing is coming out of the aircraft horizontally. They also say it as a UDL. Now, a uniformly distributed load, or UDL. So it's just a spread out weight, and it's 4 kilonewtons, or 4,000 newtons per meter. So every meter we move along, we would have, and they've put the little humps here like this, but they're actually putting them on the wrong side, because this would mean that it was being weighted from this side. And of course, we know that's not the case. So that's probably a bit of an error, I think. In the textbook, we really should have our UDL going this way. We know that our beam as a whole is 2.5 meters, or sorry, our wing, it's a wing, and it's being pushed up. And you can convert a uniformly distributed load to a point force acting at the center of that uniform load, okay? So that would be 1.25 meters, because 1.25 meters plus 1.25 meters, you got it, is equal to 2.5 meters. Okay, so it's acting at the center. Now, how do we work out what that equivalent point load is, a single point load? What you do is, it's really simple. You just say the point load is equal to UDL times the length of the beam that we're dealing with, or the length of the UDL that we're dealing with. So, you know, if you had a beam that had a UDL just here like that, and you worked out its equivalent point load, it would be acting at the center of that little cluster of UDLs. Okay, so in this instance, it's going all the way along the beam, so we can assume it's just acting at the center of the beam. So we go, that's going to be equal to 4 kilonewtons, because that's the UDL, times the distance, which is 2.5. So we end up with an equivalent force of lift, essentially, of 10 kilonewtons. We're going to put that an L there for lift. So that's how we work out our point load. Then now, for this question, they want you to work out the bending stress. But to work out the bending stress, one of the values that you need to know is going to be the bending moment. Okay, so we need to calculate our bending moment. We've done shear force and bending moment diagrams. Okay, so we're going to do it using that knowledge that we have of shear force and bending moment diagrams. So now that we have a point load, what we're going to do is we're going to draw our shear force diagram. That's the first one we draw. So we go like that. Before we do that, we need to work out our reactions at the wall. Okay, so if you remember from our Year 11 work, if we have a force acting up here, it's going to be acting up all the way along this beam. Okay, now when it gets to the wall, if there was no force acting as a reaction to that, the beam would want to go shooting up the wall. So there must be something holding it down, and that's the reaction at the wall, which is here. Okay, so I'm going to call it RW. Now the value of that is going to be equal and opposite, so that our forces vertically are going to be in equilibrium, because otherwise our beam would go shooting off into space. So we know that our reaction at the wall is going to be equal to 10 kilonewtons going down. Okay, so that's our reaction at the wall. Now the force is pushing up, so if we have our force pushing up and it's fixed here, it would want to be rotating this way. Okay, so now for our force going up, we said we had to have equal and opposite force going down. It's the same, so that's a balance of forces. We know that the system in equilibrium will have its moments in balance as well. So if we have an anti-clockwise rotation wanting to happen, the reaction at the wall, the bending moment at the wall, has to be opposite. So our bending moment at the wall will have a reaction at the wall of 10 kilonewtons, and we'll have a bending moment that's going clockwise to counteract the way the beam wants to be heading. Okay, so that's an explanation of those reactions. So we know with our shear force diagram that we have to follow the forces. So we have a force here, and we know its value, it's 10 kilonewtons. So we come down to minus 10. And then we go across to this halfway point, and this is the end of the beam here. So we're going to go down minus 10, then we go across, then we have this force going up, so we go up, and then we stay at 0 till we get to the end of the beam. Okay, so that's our shear force diagram for that point load. Now if we wanted to do a diagram for bending moment, we know that bending moments are equal to the area, okay, inside this shear force diagram. Now what we need to work out is, do we have a positive bending moment or a negative bending moment? We know that if you follow the forces, you end up with a negative shear force anyway, but you also know that this is a negative shear force because of the sign conventions for shear force. Okay, so sign convention shear force, okay, which is if you have a section where the forces are wanting to rotate the object clockwise, it's going to be positive. And if you have a shear force that's trying to force it in an anti-clockwise, it's negative. Okay, so that's why we end up with, this is pushing up, and this is pushing down, so it's going to be turning in that direction, which is anti-clockwise. So we know that's why we end up with a negative. But if you follow the forces, you end up with that anyway. But then when we go to the bending moment, we don't have that follow the forces because we just know that it's an area, okay, the area of the shear force diagram. So is it a positive moment, a bending moment, or a negative bending moment? So we need to know the sign convention for bending moments. Okay, so remember we talked about this is a really simple, if the beam is smiling, it's positive, and the beam is frowning, it's negative. So with your wing, it's being pushed up, okay, which basically means if you were to do a mirror image on the other side, it's a smiley beam, so it's positive, okay. If the beam is pushing down, it would be negative. Another way of that sign convention, working with that sign convention, is just saying if you have a section, if the bending moments are doing that, it's positive, and if the bending moments are doing that, it's negative. Okay, so looking at this particular drawing here, we know that we have a smiley beam. Okay, so it's going to be a positive value. So we basically say 1.25 times 10 is going to give us a value of positive 12.5 kilonewtons. Okay, now that value of 12.5 doesn't go straight across. It goes to this point here, boom, and then it stays at 0 to the end of the beam. Okay, so that is our bending moment diagram for this point load. Okay, so we've covered quite a few things there. We've covered taking our point load and putting a reaction at the wall. We've worked out that our bending moment at the wall has to counteract in its direction the actual force direction, it's called the direction of rotation that the force is trying to cause. So in this case, it's trying to make us go anti-clockwise, so our bending moment has to be going this way, okay, for it to work. And that's how we ended up with this diagram here. This counteracts our 10 kilonewtons of lift. So our reaction at the wall is down, and now this is counteracting the fact that the beam wants to go in that direction. Okay, so transfer your force to the wall to find its reaction. Make sure your bending moment's counteracting the direction that the force is wanting to make the beam go in. And then follow your forces, okay, for your shear force diagram. Follow the forces. And then your bending moment, you need to ascertain whether you're dealing with a positive bending moment or a negative bending moment. Smiley beam, positive. Sad beam, negative. Okay, so that is the diagram if you're dealing with a point load. What we're going to do now is quickly solve the problem. Once we know our moment, we use our formula and we're just going to plug it in. So we said we have a wing, and the wing, they've said, has a neutral axis, and they've asked you to work out the bending stress for this wing. Let's read it here, bending stress. Find the bending stress, bending moment. So they've asked you to find the bending stress, okay? So I don't know if they've told you on the lower surface, okay? So now you need to use that formula. Bending stress is equal to my over I, okay? So we've worked out our moment, okay? That was our bending moment, okay? So that was that value there. Y is the distance from the neutral axis. So they've said this wing from the neutral axis, okay, which is that little dotted line, to the lower surface, we end up with 20 millimeters. Okay, so that's this value here, and then I is the second moment of inertia. They give you that value. Okay, so basically what we have to do now is put all of those values, but express them in terms of the standard units. So our bending moment is 12.5 kilonewtons, which is 12,500 newtons. We need to multiply by Y, which is this value here, distance from the lower surface to that neutral axis, and 20 millimeters in meters, you divide by 1,000. Okay, so you end up with times 0.02, and you divide the whole thing by this value of I with the second moment of inertia, which they give you in the actual question. Okay, they're always going to give it to you because it's too hard to calculate in high school. So your I value is equal to 2 by 10 to the minus 6 meters to the power of 4. Okay, so we just put that value on the bottom. And when you do all your working out, you end up with a really big value if you're expressing it in pascals. We're going to express it in megapascals. We'll write it in pascals first. You end up with 125. You end up with 125 million pascals, which is 125 megapascals. And that is the answer to the question. We've gone through quite a few things there. We talked about sign conventions for shear force. We talked about sign conventions for bending moments. And we've worked out the bending stress on the lower surface of this aerofoil. Hopefully that helps. Now we're going to go into SkySieve and look at what that bending moment diagram will look like for a point load, like we've done here, to check whether we got it correct. And also we're going to check to see what it looks like for the actual UDL. See you in the next video.